Emmert International was awarded a contract to remove 4 spans of the old Sellwood Bridge as part of the Sellwood Bridge removal project. The Sellwood Bridge, which spans the Willamette River in Portland, Oregon, was opened in 1925 and was the first steel truss fixed-span 2-lane bridge in Oregon. After many years of monitoring the condition of the bridge, it was determined that deterioration was continuing at a steady pace. The old Sellwood Bridge would be replaced with a new deck arch bridge, which opened in 2016. Emmert International was tasked with devising a method to lower all 4 bridge spans to a barge. With extensive engineering analysis and research, Emmert International carefully chose and designed the most ideal method of rigging to meet the demands of this challenging disassembly process. Prior to the start of the project, operational and technical review meetings were held with all parties involved to ensure all project activities were well planned and coordinated, including site training and safety meetings. Bridge spans varied in weight and size. Span 17, 199 feet by 23 feet by 33 feet and weighed 390,000 pounds. Span 20, 246 feet by 23 feet by 33 feet and weighed 476,000 pounds. Span 18, 246 feet by 23 feet by 33 feet and weighed 476,000 pounds. Span 19, 190 feet by 23 feet by 33 feet and weighed 372,000 pounds. Challenges to the project. The challenging task of lowering each bridge span to the barges below required detailed engineering and creative use of equipment and time management to address environmental and safety concerns. To ensure safe and efficient operation, specifically engineered components were designed and selected to work in conjunction with the Strand jack system. All components of the old bridge, including piling, had to be removed by July 30th due to a state-imposed fish window. In the event the schedule could not be met, the work would be postponed for 1 calendar year. Had the work been postponed, heavy liquidated damages would have been assessed to the project. The work hours were limited each day due to a traffic window. The restriction made it all but impossible to make up for any lost time. Noise abatement for surrounding homes imposed limitations for hours of operation, adding further time constraints. Keeping the new bridge open during all operations was carefully planned for the safe integration of the workforce and public. Tidal constraints were a leading factor during the east and west bank truss removals. Low tidal conditions complicated barge positioning during the lowering process. To prevent the barge from touching the river bottom, each span had to touch down on the barge during the high tide and then repositioned into deeper water before the tide receded. Seasonal winds posed an impending delay threat. Multiple days saw wind gusts above engineered specifications for the lowering process. Due to days lost from weather conditions, contingency days were utilized. These contingency days were preemptively programmed into the project schedule to mitigate possible liquidated damages. The old Sellwood Bridge had a coating of lead paint. When cutting or grinding, lead paint containment protocols were required to be followed. Emmert limited the lead paint issues by developing attachments that did not require welding. Spill containment systems were placed at each Strand jack location. Emmert also assigned a specific person at each jack location to monitor the jacks for any abnormalities, should they occur. The bridge was inspected daily for nesting birds to ensure no harm came to migratory bird populations. A bathymetric survey was performed on the east and west sides of the river. The survey and the abnormally low water helped determine the best barge size and position for the span removal. All ballasting operation was done utilizing a fish weir to assure that juvenile fish and other marine life were not drawn into the pump. The bridge spans required to be removed in a set order. This was to control the camber and flex in the existing spans during removal. To control the overall deflection, the spans were removed in the following order: span 17, span 20, span 18, and finally span 19. The concrete deck of the bridge had previously been removed, creating an extreme amount of camber. To safely cut the bridge into removable spans, a specific cutting plan was established. By following the established sequence, shock loadings and strong shifts were mitigated during the cutting process. Each span required its own cutting sequence. Design. There were two methods proposed for supporting the modular strand jack system, one a tension and the other a compression method. During Emmert's first review, compression struts were considered for supporting the strand jack system. After a detailed review, tension struts were chosen to reduce the amount of grinding and welding by building movable attachment brackets. All the brackets were put into place before the bridge was closed. This allowed the team to install all strut sections needed for the lowering of the spans outside of the critical path. T-brackets. To eliminate welding, Emmert International designed custom T-brackets. This approach reduced lead paint abatement on the bridge. Because the lifting lugs were fabricated in our shop off-site, the testing was performed in a controlled environment. This helped the project schedule by removing this work from the critical path. Modular strand jack support beams. Custom designed box beams with strand jack rocker plates were engineered for the rigging lift system. These rocker plates allowed the strand jacks to rotate as needed to accommodate movement in the bridge span during the lowering operations. Access holes were installed strategically into the sides of the beams to allow access to the bottom of the strand jacks for easy access and monitoring of the strands. Execution. Prior to installation of the custom-designed modular lift system, extensive pre-work was performed on the existing bridge. Pre-installed bracing and pre-tension members were installed and inspected several times by Emmert's field engineer. Ongoing inspections were performed throughout the strand jack installation to ensure no interference would occur during the lowering operation between the standing structure and the structure being lowered. The modular strand jack support beams were designed by Emmert International to meet several objectives. The beams were designed to be set up quickly by the rigging crew while maintaining the highest level of safety. Due to the location of the old bridge adjacent to the new bridge, the operation was constantly monitored by both Emmert International and county officials to ensure a safe operation during the setup and lowering operations. The safety cabling system designed by Emmert International was reviewed by the Project Safety Committee, which commented on the ingenuity. The design system was approved for all phases of the lowering operations. The beams were pre-assembled with all the lifting components prior to being placed. This included the strand jack rocker plates, strand jacks, heavy lifting strand guide umbrellas, handrails, and an overhead safety cable. Once the areas were inspected and cleared, Emmert International installed the pre-assembled strand jack support beam system. The assemblies were installed in predetermined lift points at 4 locations and secured to the existing bridge girders by the engineered DWDAG hold-down plate system. The strand jack anchors were then connected to the specially designed T-brackets that were pre-installed on the bridge spans. The T-brackets were designed to be as light as possible while meeting the structural requirements of the ASME BTH-1. The assembly received a final inspection prior to the barge being placed and the bridge span lowered. Bridge span cutting procedures and pre-installed bracing received a final inspection. Confirmation was given, and all environmental, river traffic, and roadway traffic control measures were in place. The strand jack system was preloaded and hydraulic pressures checked and verified. All connections and components of the system were checked for deflections and abnormalities. Acceptable wind and weather conditions were reconfirmed prior to the lowering process. As these verifications were taking place, the deck barge was moved into position to receive the bridge span. The bridge span was cut free from the bends. Final checks were performed to confirm no obstructions during the lowering process. The bridge span was lowered to a pre-aligned barge. Once the span was fully supported by the barge, the strand jack anchors were released from the T-brackets. The bridge span was secured to the barge and repositioned to avoid river traffic. The modular strand jack base assemblies were moved and installed in the predetermined locations for removal of the next bridge span. This process was repeated until all 4 main bridge spans were lowered and removed. The east and west end spans posed a special set of challenges that needed to be overcome by a detailed site-specific marine plan for both shorelines. The rigging plan was specifically altered for each span to meet the geographical conditions at each shoreline. One of the requirements in the marine plan is that the barge may not touch the bottom of the river during any of the operations. It was also required that the spans cannot harm any of the vegetation along the river bank. The east end span extended over the slope bank shoreline. The bathymetric survey for this area concluded the span to be set off-center on the barge due to the bank's shape and low water conditions. During the lowering operation, both rigging crews, one operating the strand jacks and the second crew waiting to receive the load on the barge, were in constant radio contact with the bridge operators and river patrol to assure a careful and safe operation for workers and the viewing public. Once the span was close to the barge, the 4-strand jack lowering operation was halted. The plan now required the river end of the span to be lowered while the shoreline end was held. This allowed the bridge span to align and land on the pre-stage landing platform on the barge that was needed to clear the river bank for span 17. Final transfer of the bridge span from the strand jacks to the barge was closely coordinated with the barge ballasting operation. EPA and county inspectors were also present to ensure compliance with the span not touching the bank vegetation. The location of span 17 requires that the barge CG be offset towards the bow. Through extensive pre-analysis and research, Emmert International was able to complete the project safely and without incident. Safety considerations. Public safety. Viewing areas were designated and barriers installed. Emmert supplied experienced and certified operators and riggers. Safety support staff and field supervisors were on site confirming the established safety plan was being followed by both contractors and public viewers. Site-specific safety training was conducted both prior and during the project. Daily safety briefings were conducted by Emmert with all contractors. Equipment inspections and maintenance were performed daily. Custom-engineered fall protection cable system for strand jack support beams. Permit requirements: EPA, Army Corps of Engineers, River Patrol, Oregon Fish and Wildlife. Equipment: HSL 2000 heavy lifting strand jack system, custom-designed strand jack bases, custom-designed T-brackets, custom-designed staging platforms. Project planning. Prior to bridge span disassembly, 785 man-hours were dedicated to planning, analysis, and engineering. Emmert International took time to carefully design lift parameters to meet the needs of the client and the associated authorities. Extensive analysis and research was done to choose the most ideal methods of rigging to meet the demands of each individual bridge span. Contract. Fixed price. Conclusions. Planning man-hours, 785. Execution man-hours, 2,820. Total man-hours, 3,605. No incidents, no accidents, no damage to cargo. All operations were safely performed under the care, custody, and control of Emmert International.